All right, so I think we can start. And today is our pleasure to host Professor Lydia Patton. Lydia is a professor of philosophy at Virginia Tech, and Patton's work centers on theory testing and on differential equations and their use in physical theories, especially fluid dynamics and gravitational wave astronomy, and has been published in journals, including Studies in History and Philosophy of Modern Physics, Synthèse, The Monist, History and Philosophy of Logic, and Historia Mathematica, and in dozens of edited collections. She's the editor of HOPOS and with Walter Ott of the collection of Laws of Nature. So Lydia, please take it away.
Yes, thank you very much. And I'd like to really thank the Black Hole Initiative and Fabio Pacucci and Achilleas Porphyriadis and Nicole Grenier for organizing this and doing such a wonderful job. And I feel like I'm in such excellent company in this colloquium series, and thanks very much for the opportunity. I'm also I'll say by way of prelude as people are filtering in that I've always been interested with respect to gravitational wave astronomy, and especially to the new results that are coming in the interplay between formal reasoning and empirical reasoning, observation and experiment. And I feel like every time I learn something about a new or a sort of broadly used instrument in astrophysics, I learn some new way that theory and experiment are being related. And so this is one case where I think population synthesis is one case where I think that's particularly interesting. And so that's what I'm going to focus on today. So let me start sharing my screen. And we'll get started. Okay, so this talk is focusing on the question of population synthesis in gravitational wave astrophysics. And you can see here a poster from a 2010 conference that I'll mention in a second. Population synthesis has grown in tandem with the development of gravitational wave astrophysics, as the ability to synthesize binary or two-body populations has kept pace with the ability to detect such systems. And this is a poster on the right here of a 2010 conference at the Space Telescope Science Institute. It just happens to have a cool graphic and lots of interesting speakers, but you can see this is from quite a while ago, even before some of the LIGO results. But there's already, at this point, stellar populations and population synthesis were a rich and growing area of research, and we're going to be looking at that in a moment. So in this talk, I'll begin by presenting the basics of population synthesis insofar as I'm aware of them, and then we'll turn to three distinctive elements of the methods of population synthesis that I want to focus on briefly. Comparisons with large-scale stellar maps, the use of dynamical equations, and calibration with other results and methods. And these all raise a key question. We might think that the methods of population synthesis, especially when they're used to calibrate or in comparison with other formal methods, raise the issue of problematic circularity. And we might see these methods as raising a problematic circularity, and we might see them as contributing to robustness. And so I'm going to be looking at that question of robustness versus circularity, and I'm going to be arguing that this is really kind of a false dichotomy, and that population synthesis can contribute to the construction of what I'll call path-dependent frameworks, which are broad frameworks for testing that allow for comparison, cross-validation, and so forth. So these frameworks allow for verification of formal methods, replication of empirical results, and cross-checking between them, and thus allow for robust connections to be made between formal and empirical methods. And so the issue of robustness versus circularity, I will argue, is sort of dissolved when we start thinking instead about how to build frameworks that are robust and are not circular out of these different methods. And I want to argue that most of the time, that's actually how these methods are used. And it's, in fact, a very beneficial and fruitful kind of feedback loop that happens. So let's see how this works out. So in answer to the question of what is population synthesis, there are a lot of different presentations in the literature. I found one in a recent paper from recent-ish paper from 2012 that's cited here. And the basic idea behind population synthesis is it's a kind of simulation of a stellar system. But in fact, as that system evolves in time. So this is a quote from this paper: "Every real or realistically simulated stellar system is a set of stars born at different times and positions with different velocities, masses, and chemical compositions." And in this paper, and elsewhere, these are called the composite stellar population. And in order to completely define the parameters for this at a particular time, at a generic time, we need to specify the distribution in space of the masses and metallicities of all of its members. So we need to talk about like which metals are found in the stars, how quickly do the metals burn up, so how quickly do the stars move through their evolution, their lifespan. And so completely defining the parameters of a particular stellar population actually involves also specifying the evolution of that population in time. And this results in an extended phase space. So the stars evolve with time, that is, they continuously move in space, lose mass, enrich in metals, and move in the phase space. So in order to actually synthesize a population, it's necessary, in fact, if you're going to do a good job of it, of explaining how this population evolves through time. So as time elapses, the stellar population is going to age. So you can start with a sort of set of initial values, like stars that have a certain composition and are at the beginning of of the main sequence. And they are formed in a chemically homogeneous medium. This is the interstellar medium at the beginning of evolution. So this is a kind of set of assumptions that are made at the beginning. And then as time elapses, the stellar population ages. According to their mass, the stars eventually leave the main sequence and soon after die. They go supernova, or they enter a quiescent stage and therefore are white dwarfs. This is a review for many of you. Injecting metals into the interstellar medium in the form of supernovae or quiet winds. And so basically, this is a simulation of how star systems evolve, so that the stars themselves are moving through an evolution, right, are moving through a sequence in which the materials that make them up are burned up, and in which there's a number of phenomena, convection and tides and so forth, that we'll talk about in a second. But also they're interacting with the surrounding medium and with other stars and other objects, right? So this is a system, a complex system in which there's a lot of feedback and interaction. So for instance, the interstellar medium becomes richer in metals, and there's a relationship between age and metallicity that gets built up and that can then be modeled. Now this is just a very, very basic diagram. It honestly comes from a children's website. It's kind of, these have to be smart children, I have to say, but the idea behind this is plotting stars on the Hertzsprung-Russell diagram shows that star populations differ in age and metallicity. So there's a distinction between a population that's young and metal rich and old and metal poor. And then you can sort of model some of the various properties of the population and how it's going to evolve over time. So just to sum up a bit, population synthesis integrates a number of factors. One is an overall picture of an ensemble of stars as they age and as they interact with the interstellar medium. Another is predictions of the mass, metallicity, distribution, and other properties of stars and how this changes over time. And finally, although not exhaustively, information about the dynamics of star evolution, including tidal and orbital motion and black hole formation. And all of this information can be very helpful to have. Now, of course, these are all simulations. right? So these are all simulated values, and the idea behind this is that you can feed these population synthesis codes, and we'll talk about one of them in a second, into a computer, and it will, after some time, yield a result in terms of the simulated population, the simulated cluster. And this can then give you predicted values for stars over time, and it can give you predictions for what's going to happen in the evolution, in stellar evolution. So this has led to a field called evolutionary population synthesis. And I should mention the groundbreaking work of Beatrice Tinsley in the 1970s and 80s that's been fundamental. I focused in my research on the Star Track code. This is not the only available code, but it's one of them. The Star Track code that's from Krzysztof Belczynski and his collaborators. There are 3 papers. I'm happy to give the references as needed from 2002, 2008, and 2010. Now, one thing that's important about these 3 papers is, again, you'll note from the dates, these were before the LIGO results, the LIGO observations and the other observations. But many of them you can tell are in fact kind of gearing up for binary system detections. So I should just say, like I said at the beginning, population synthesis methods, like people were aware who were working in population synthesis that like the binary system detections were being prepared for, and that the observatories were being built and so forth. And so there was a real effort to predict what binary systems would appear and what their parameters would be using population synthesis methods. But I should emphasize here at the beginning that population synthesis methods are much more general than that, right? They deal with all sorts of stellar systems and clusters and ensembles. So these are some of the ways that Belczynski and his collaborators use population synthesis. They track the evolution of star formation, binary formation, and mergers. That's not surprising. There's also information about the rates of formations of stars, right? So you can talk about predicted rates at which stars will be formed and stars will either merge or go supernova or whatever. And that information can be very helpful in predicting like how many systems you expect to encounter in a particular area. Learning about the global properties in general of ensembles or star systems. This can be very interesting information in terms of just predicting the sort of large scale behavior. Analyzing the parameters of known and predicted systems, that's what it's sort of designed for. Making predictions about the systems that will be observed. This is what's been very helpful in the case of LIGO and others, and comparison with maps of known star systems, which we'll talk about in a moment. So this is just a kind of list. It's not a comprehensive list, but this is a list of ways that population synthesis has been used in the literature, in these papers and others, even before the recent observations of binary system mergers. Okay, so I'm going to focus on 3 specific features of population synthesis before getting into the main question of the paper. But I think these features are interesting in and of themselves. The first is the way that population synthesis is linked with kind of empirical observations or data. So the first method I'll look at is large-scale map comparison. So there are these amazing large-scale maps, the Bright Star catalog, which you'll see in a second, the Hipparchus catalog. There are other efforts to make large-scale maps, the EHT, others that are mapping the sky, right? Mapping the universe. And so one way in which to give an empirical check or a check against empirical observation of the results of population synthesis is, and this is from Hurley, Poles, and Tout in 2000, to reproduce the findings of large-scale star surveys, right? So of course, that makes sense, right? If there are large-scale star surveys that have actual observed values for particular stars at different stages of evolution, and also information about the sort of large scale properties of these systems, then one way to give a check of population synthesis methods is to see if the population syntheses like match up with these known maps, right? That's an obvious case where there might be an empirical comparison. So here, you might try to reproduce the findings of star surveys like the Bright Star Catalog and the Hipparchus Catalog using population synthesis. So a goal of this is to show that the equations and assumptions that are used in population synthesis yield results that replicate the findings of large-scale surveys. So one thing that's going to be important here is that those surveys give you kind of a, they give you information about what's been observed and at which times and the evolution of systems. It doesn't give you kind of complete information in the way that population synthesis does because you only observe at particular times. But the idea is if you can make the population synthesis sort of replicate what's going on in a map, then that's a check, that's an empirical check or verification of the population synthesis methods, at least insofar as there's an overlap between the two. So this is just an example of the Bright Star Catalog, and this is the mapping. And so the idea is, again, if the population synthesis sort of matches up with what's given in the Bright Star Catalog, then that's an empirical check. To be honest, I just gave you this slide because it's pretty. I'm not going to be able to tell you what's going on in each place, but this is the idea. Okay, so one purpose of population synthesis then is to try to replicate the findings of maps of galaxies and star systems. And these may feature detections that have already been made, or sometimes the maps actually give you predicted values as well as detections. Population synthesis, so importantly, I want to point out there's actually a kind of feedback that isn't often mentioned, but that does happen. I have found it. Population synthesis itself can serve as a check or comparison for the maps, right? So it can be the case that you have a map and there's like part of it that you're not really sure what's going to, what happens beyond a certain limitation or boundary, right? Or you're not sure what the objects on the map are going to evolve into, or you have some set of static results on a map and you're not sure exactly how to put them into a larger picture. And of course, that's exactly what population synthesis is designed to do, is to give you an account of the evolution of the system, not just observed values at a particular place. So one important point is that it's true that map comparison can give you a kind of empirical check on the values of population synthesis, but conversely, population synthesis can also tell you what to look for in order to look for like a future evolution of the system, or to look for values beyond what you've got on the map. So this can make a rich source of information, the maps, even richer. But this also leads to the second set of methods that I want to talk about, which is dynamical equations. I'll be very brief about this. This is, as Fabio Pacucci said, this is part of my research, but I won't talk a lot about it. Population synthesis is based on dynamical equations and reasoning, resulting in a picture of the evolution of star systems in time, in phase space. And this picture also involves the interaction between system elements and how these change over time. So we've already talked about, for instance, the interaction between the interstellar medium and stars as they go through the main sequence. So as stars are going through the main sequence, they're sort of giving off metals, they're losing mass, and this is enriching the interstellar medium. That material is also being picked up by other bodies. And so there are these really complex dynamical relationships that are happening. And these need to be picked up by the equations and predicted by the equations. And so as you saw in the beginning in the presentation of population synthesis, it's a fundamentally dynamical method. It's talking about the evolution of a system. So when you hear population synthesis, you might think, especially if you're using the kind of analogy from biology, you might think, oh, this is where we're talking about like how many birds there are and what kinds, but then just moved over to the astronomical case where we just talk about how many stars there are and what kind. But one important, really, really crucially important part, again, just to emphasize this, of population synthesis is the evolution of systems over time and how exactly those equations predict that evolution. So to take an example, this is a kind of fundamental paper in the field, sometimes called HPT, Hurley, Poles, and Tout. I apologize if I'm mispronouncing their name. It was in the memoirs in 2000. A fundamental tool in understanding stellar evolution is the Hertzsprung-Russell diagram, which provides a correlation between the observable stellar properties of luminosity and effective surface temperature. The HPT formulas, which are widely used, including in the Star Trek code that I mentioned earlier, find analytic approximations for the highly non-uniform movement of a star in the Hertzsprung-Russell diagram. Now, finding general analytical formulas is more difficult than just interpolating between values of a table. So we could, one could just take a table of results that are already there and just say, well, let's just use interpolation to predict what's going to come in between the values. Now, it's much more difficult to say, instead of just interpolating between these values of the table, we're going to construct a system of dynamical equations that if you feed in some sort of hypothetical values for what's going on in the system, you're going to get a set of predictions for what's going to happen in the system. Now, that's going to be much harder, but that's in fact what the HPT paper tries to do and seems to have succeeded at doing. So this is an example of the evolution, the Hertzsprung-Russell diagram. If you're into those, I'm just providing it. I'm not going to go into detail, partly for reasons of time and partly because I'm not actually capable of explaining this diagram in detail. I'll just admit to that. Okay, so the third set of methods that I'm going to talk about is calibration. And this is where things get interesting from the perspective of, really interesting from the perspective of the question that will be my main focus. So one of the important points is that as you saw earlier, population synthesis is calibrated or checked or validated by observed results found on maps. But it's also true, I've found in looking through the literature that there are cases where population synthesis is actually used as part of the ways of simulating systems that will then be looked for in detection, in searches, right? So not only is population synthesis calibrated using observed results, the methods of searching for new systems are sometimes calibrated using population synthesis, because the idea is, well, population synthesis tells us where to look. It tells us what kinds of stars at what stage in evolution would be expected, or what rate of star formation and so forth would be expected in a certain region. So for example, parameters used to generate templates for template-based searches may be tuned using predictions from population synthesis. And I found a couple of papers, Belchinski et al. In 2008, and a couple of other papers have mentioned this, which I find very interesting, because again, this is kind of moving in the other direction. Secondly, the equations used to generate templates or to model binary systems generally may be tuned using dynamical reasoning based on population synthesis. So people might think about the way that population synthesis sort of models stellar evolution, or the interaction between elements of a stellar system, and think about that in generating templates, or in generating simulations in terms of what kind of systems to look for when conducting experiments. Finally, reasoning about initial or boundary conditions, or about possible detections in general, may be calibrated based on population synthesis, or vice versa. So I found several papers where people say, well, you know, we think that the boundary conditions will be like this because of results from population synthesis. And here often the population synthesis will be based in a sense on already known empirical results, right? But so the equations will be kind of constrained or limited by empirical reasoning. But nonetheless, it's the case that population synthesis can actually be used, and at least theoretically and potentially much more broadly, in order to reason about the evolution, the possible evolution of a system. So it's a kind of really interesting way that in the future population synthesis could be used to make detections more, to be able to simulate a broader set of possible systems to detect, and to be able to focus sort of searches and attempts to detect new systems. So that's kind of an exciting way that population synthesis could be used. And I found some cases where it is used this way, although not a ton, right? Okay, so here's the thing though. So we're now starting to move into the second part of the paper. Calibration requires being able to relate population synthesis methods to systems that might be detected. And here I said using template-based searches, but they don't have to be template-based. It's just, if you're gonna use this kind of feedback between population synthesis and methods of detection that I've been describing, you've got to be able to relate the two systems to each other. So what are some ways that can happen? Methods of population synthesis may be tuned to or calibrated by methods for searches or post-data analysis, and vice versa, right? So there are ways of sort of connecting these two systems, the system of observation and detection and the system of population synthesis. So for instance, the parameters of systems that are predicted by population synthesis might be used to focus methods of detection. And this is a use that I've seen mentioned quite a bit, is like, you know, population synthesis tells us that there must be a bunch of stars in this particular part of the galaxy, right, or something like that. Or the parameters of detected systems may be used to inform population synthesis and the inferences drawn from it. So if you've got a detected system, then that will be able to kind of, that observation can then become one of the empirical results that then is used to either verify or falsify the predictions of the population synthesis, right? So if you say, well, here's a system that's actually been detected, and it turns out that it's not exactly like the system that would have been detected if these equations were right, then you can kind of fiddle with the equations or fiddle with the parameters or variables in order to get a better prediction, right? So there's a kind of feedback between the two. So methods of prediction via population synthesis are used to tune, or can and probably should be used to tune search and detection methods. So for example, a range of hypothetical mass or metallicity parameter values may be used for population synthesis. And then when a star or black hole is detected, the detection may provide evidence that it actually has those values. And that's then the basis for post-data parameter estimation. So it might be the case, for instance, that population synthesis tells us to look for a system with certain properties, certain parameters, and then scientists actually find a system or a star that has those properties and those parameters, and we say, great, like this is what we were looking for. But is that circular? There's a risk of circularity in the sense that parameters generated by population synthesis might be fed into the detection system. So you might say, okay, we're looking for a system with these particular parameters based on assumed values that were fed into the population synthesis code in the first place. And then after detection, fit to those same parameters is used to confirm that a system of that kind was predicted by the theory or model being used. So we might say, well, we were looking for a system with these particular parameters and we found it. But you might say, well, but if population synthesis is being kind of used in the methods of detection, then isn't that potentially circular? And I'll try to focus that a bit in a second. So one example might be luminosity. This is a kind of interesting parameter. So in population synthesis, the luminosity of a star is related to the extent to which the metals within the star are consumed. So this makes sense, right? Is that how bright a star is going to be based on how much of the metals within the star, how much of the metals and gases within the star have been consumed along the main sequence. And this is, so luminosity is one of the key values on the Hertzsprung-Russell diagram. Now, interestingly, in searches and detections, luminosity is an observed parameter of star systems. So it's when you're detecting a system, the luminosity is something that's observed, that's related to other properties of the system, and that actually can sometimes be considered degenerate with other parameters like distance, right? So clearly, something could be a system that is bright and close, or it could be dim and far away, Or it could be that we think that it's bright and close, but it's, you know, you get the idea, right? Like the distance of a system and its luminosity can be degenerate with each other. We could make a mistake because we think that a system is close to us because it's bright, but it's actually huge and bright, and it's farther away than we thought. Now that's it. That's the idea. So in this case, when we look at luminosity, what's actually happening here is that notice that it seems like if we're looking for a system with a certain luminosity that was predicted by population synthesis, and then we detect that system, it's actually not the same thing, right? So this is something I just want to point out. Like here, luminosity as it's predicted by population synthesis and luminosity as it's detected by observation are actually two quite different things, and they're estimated in quite different ways. So here I want to start arguing that, in fact, what's happening in the use most of the time, not all of the time, but most of the time in the use of population synthesis to sort of buttress or support detection methods and observation methods is a form of robustness. So I've given this like excessively complicated feedback system here where I'm saying, look, we might start with a bunch of analytic formulas and feed them into like the HPT formulas and feed them into a code for population synthesis. Then we get models of evolution. We constrain those using previous observations. And then that gives us new models of evolution. This then yields a population synthesis. There are then observed checks on that population synthesis that tell us about what's actually been observed and whether that fits with the predictions, which then those checks and those constraints then yield new analytic formulas, and so on and so on. Now, one of the things that's interesting here is that all of this feedback between models and checks and empirical data and new analytic formulas and so forth is certainly a form of what I'd call path dependence, in the sense that things further down are dependent on decisions that were made further up or on reasoning that happened further up this chain. But I'll note that path dependence is not necessarily circularity. Sometimes it can be. And so if you, I don't think that this will be a problem, but if anybody wants a good question to ask, like one of them would be, what are the cases where there's circularity? But I don't think that path dependence in this case actually means that there is circularity. Why not? Well, circularity, there are bad kinds of circularity. So like Jamie Elder in, oh, that is a mistake. This says 2000, it's actually 2020. I made this this be a much more venerable result and less fresh than it is. It's an amazing new work from Jamie Elder 2020, where Elder argues that model-dependent observations used to confirm are then used to confirm the very same models, right? So this is a new result, that a new argument that what can happen in some models for gravitational wave astrophysics is there's a potential problem, and Elder points out that there are ways of resolving this, where observations that are dependent on a certain model may then later be used to confirm those exact same models. That seems to be a problematic circularity. But I want to argue that in situations like this one with population synthesis, what seems at first to be circular reasoning is actually path-dependent reasoning of the kind that I've just described and that I'll go into more detail about in a second. And path dependence here, what I want to sort of focus on in the case of path dependence is that there's a kind of cross-framework reasoning, or a kind of chain of reasoning, where we say, okay, we want to look at a system of equations and then look at how there are empirical checks on those equations or constraints on those, and then generate a set of models using those initial values or empirical data, and then generate a set of predictions, et cetera, right? And as time goes by, and as that kind of reasoning goes on over and over, it's true that there's a kind of circularity, especially if you sort of look at that cycle in a particular time, in a particular time slice. But what in fact happens over time is that you build up, ideally, the basis for cross-framework comparisons that can be made much more quickly and easily over time, where systems can be tuned or calibrated in terms of each other, but in a productive way, in a way that allows for simulations, detections, estimates, for productive feedbacks between observations and theoretical reasoning. And in other words, for a broader framework for allowing empirical testing to enrich theoretical reasoning and vice versa, right? So the argument is that ideally, path dependence doesn't lead to circularity, it leads to building up a more robust framework for kind of making these decisions. So population synthesis, for instance, may inform a particular framework for making inferences about the kinds of systems that may be detected. And observations, for instance, LIGO's detections, inform population synthesis in turn, right? Like they're used as either confirmation or falsification of the predictions. Now, these observations are then going to be model dependent, right? I mean, all observations in this kind of astronomy are going to be model dependent to some extent, right? And so we might think, there's a circularity, right? People knew where to look because of these models that were already informed by a robust set of assumptions. And then they confirmed using highly model dependent methods, they confirmed some detection. And then it turns out that what was found was just what people were looking for. And then it seems like that's circular reasoning. But one thing that I want to really emphasize in the particular case of population synthesis is that the frameworks are not the same. And I mentioned this briefly earlier in the case of luminosity, but now I want to make that point much more broadly. So reasoning using population synthesis is often, almost always, going to be at least partially and possibly largely independent of the kind of reasoning that's used in template-based searches and in other types of detection. And this is enough, I want to argue in closing, to build a robust framework for comparison and cross-validation. So population synthesis works using equations describing the evolution of star systems in time, using variables like luminosity, metallicity, position on the main sequence. Template-based searches work using templates generated with dynamical equations describing the physics of binary systems, plus estimates of parameters. And those parameters are going to be like the chirp mass, the orbital period, angular momentum, and so on, mass ratio. And these parameters, you'll notice, are partly independent. So the equations are going to be partly in terms of parameter values that are quite different. So, for example, we might say that population synthesis simulates a specific predicted binary system with a certain mass ratio. And then if that exact system is detected, we might think that's circular. But there are different variables in play, and these variables are partly independent. Second, and I haven't talked about this much, but it's the case, there are independent means of detecting binary systems, and this is well known, right? So what I want to argue in closing is that this is a case of reinforcement, calibration, reduplication, replication, and so forth, not circularity. So just to take as an example, this is a graphic of masses in the stellar graveyard. And you can see in the description at the bottom that these are masses for black holes detected through electromagnetic observations, gravitational wave observations, neutron stars with electromagnetic observations, et cetera, right? So these are all, this is a kind of map. It's a pretty visual one, but it's a map. And you note that there are different and somewhat independent ways of verifying the masses and their detection, right? So not only is it the case that population synthesis methods are partly independent, there are also independent methods of verifying parameters like the mass of systems. So my argument here in closing is that path-dependent frameworks of this kind, like those used in the way that population synthesis works together with gravitational wave astronomy, allow formal physical reasoning to broaden the empirical base of a theory. And this may seem paradoxical that the empirical testing and the empirical base of a theory is actually made sort of broader and more robust using formal reasoning, using kind of theoretical reasoning. But I want to argue that this is something that happens over time, and this happens in a way that builds increasingly robust frameworks that benefit from empirical data and observation, yes, but it's not simply a matter of empirical checks, it's also a matter of building these robust frameworks for future research. And so that's what I'll conclude.
Thank you, Lydia. Thank you for a very interesting talk. And we have time for questions. I have a question actually to start it off. A few slides ago, you were talking about the reinforcement, not circularity, and I slightly missed what you were saying with the mass in the graveyard.
Yes, sorry. I was trying
Because
to.
I'm not a philosopher, so I'm not very familiar with these terms.
Right. So, okay, so just to say something more about how I'm using these terms, and there are others here who can talk about this too. What we might be concerned about in terms of circularity would be if there's an assumption made in a model that then is confirmed by that model. And the question is the evidence actually independent of the model, or is it dependent on, does the evidence itself actually depend on the model? And so one of the things that I was saying about it was a very simple point about that graph was just, well, in that particular case, there are independent observational checks.
Okay.
Right.
That will be the reinforcement.
That's right.
Okay.
Yeah.
So, for example, you can measure, for example, one parameter like the mass in several independent ways.
Yes.
Okay.
Right.
Okay.
And so then it's not necessary to assume that it's been built into the model. You can say, well, this part of it has actually been independently reinforced by multiple empirical methods. Yeah.
Thank you.
Thank you.
Shep.
Yeah, can you hear me?
Yeah.
Yes.
Hi. Yeah, Lydia, very interesting, provocative talk. So I wanted to ask about the number of observations and how this scales with the number of observations. So, in the Event Horizon Telescope, for example, we have 2 sources, and of course, we're overjoyed. I mean, they're great sources, we love them, but it's not a stellar population, so we can't extrapolate too much from that. We can learn about individuals, but we can't necessarily learn about the larger population. How does this scale with the number in the population? In other words, how can you quantify the uncertainty in your inferences for the population with the number you have, and does it scale with parameters of that population? And then these unknowns are very interesting as well. As Fabio put it, you can measure the mass in many different ways. One of the interesting things about stellar populations is that you can look to a distant galaxy where you can't resolve the stars and say something about the light coming from that galaxy based on the presumed population. And then you can find out what the distance of that galaxy is, et cetera, through other means. So I'm just trying to get a feeling for when you start to be very confident in your population studies.
Right. Yes. So one of the, sorry, I'm actually looking at something on paper, which is why there's a delay, because paper requires actually looking at it.
Wait, actual print on paper?
Actual paper. I printed these out, so okay. So of course I'm not going to be able to find what I'm looking for, right? But I can send the paper. But so yes, so the question is going to be, first of all, like how does this scale with the sort of number of observations, but then also with the number of parameters that you can test, right? So how does your uncertainty change depending on what you can actually back up and what tends to be hypothetical? So there, tell me if I'm wrong, but I think there's actually two independent questions there. And one of them is, look, if you can make observations of a certain set of sources, you know that those are part of a population, but you've got observations of that part of the population. And so then the question might be, well, what certainty might even perfect observations of those two sources give you about the broader population properties, right? Is that the... Oh, I think you're muted.
You're muted.
Sorry.
Sorry. So you're talking about the accuracy of the individual observations now. Is that what you're saying?
I'm talking about what evidence would even perfectly accurate individual observations give you about the broader
oh, sure. Yeah. Mm-hmm.
Right. Is that part of the question? Okay. Yeah. So that would be one question. And then another question might be, how many parameters do you need to measure in order to get certainty about that, right? So so I see those as two questions really, and related in a key way. And I think that this is going to sound like a punt, but I think it depends, right? So in the paper in the sort of comprehensive paper that I read, the article is the claim is going to be that it depends on which parameters you're measuring. But I'd have to go back and look at this again. I'm really interested in this question, and I think it might take more work on my part to really have a solid answer. But the impression that I get is that it depends on which parameters you're measuring, because some of them you're going to be able to, if you can measure those parameters with even some partial sources in the population at some particular times, then that's going to give you just a huge amount of information about the rest of the population. But then in other cases, it gives you only very limited information or basis for inference. I mean, that's going to be true in general, right? But that's the impression.
Well, I suppose over time, as you said, everything falls out. I mean, the only danger is that you build instruments informed by these population studies that are self-confirming, in some way. But we hope that's not the case. We hope that we open up sufficient areas of parameter space that, through some mixture of serendipity and increased resolution, increased capacity of our sensors, that we're able to get the full picture. And then we get these other directions of measuring mass through other means, for example, that round it all out. So we just want to make our probability of success as high as possible.
It's interesting that you mentioned mass, because that's the parameter that everybody, everybody talks about as being, if you can get that one, then that you can measure it in various different ways. You can get orbital motion, or you can, and so forth. And then that tells you a lot more information about what's going on in the system than the other parameters. But by that same token, if you get the mass wrong, you can make correspondingly huger mistakes down the line. And so that's borne out by what I've seen in this literature, yes.
Okay, thanks. Thanks a lot.
Thank you. I'll have to think about
Jamie.
that. Hi, Jamie.
Well, thank you so much for that talk. My question, I think, is just trying to sort of clarify your conclusion, because throughout you use the word robustness. And so I guess I'm just trying to figure out exactly what you mean by making the frameworks more robust. So I have a helicopter outside. I don't know if you can still hear me.
Cool.
But yeah, so in the philosophy literature, robustness is often fleshed out in terms of, a conclusion is robust insofar as you varied the evidence in various ways, whether that's to do with the measuring equipment or the modeling assumptions or whatever. But of course, there's this other meaning of robustness, which I think ties in more to sort of something being stable over, things being changed. And I get the sense that that's the kind of robustness that you're referring to when you're talking about the frameworks, but maybe you can help me understand a little bit better what you mean.
Yes, thank you for that. That's very helpful in terms of the sort of philosophical argument insofar as I have one. And I think you're absolutely right that it's the second type of robustness that I'm talking about. And I specifically didn't try to talk about things like multimodal evidence, like the analysis from Stegenga and others, because I find that a very insightful analysis, but I don't think that it's what's relevant here. These aren't questions of like, how do we take a bunch of evidence and sort of amalgamate it, or show that different kinds of evidence can be combined in order to provide stronger evidence for a conclusion. Because I think there is that problem, but that's not the problem that's found here. The problem here is there are possible mistakes that can be made, as came up with the last question, where you, for instance, are looking in the wrong place, or you're looking and you assume that a system has certain properties, you confirm those properties, but it's only because you made those a priori assumptions that you detected a system of that kind in the first place. And so the mistakes that you're trying to avoid in the cases that I'm talking about are mistakes where I'm sorry, I always mix up type 1 and type 2 error, but I think type 2 is when if there were a system present with a certain set of parameters and description, would you have detected it, right? I hope I'm right about that. But basically, that's the idea that I'm trying to look at here is how do we rule out the possibility that there's a system that has certain properties that isn't detected because there are certain assumptions that were built into the models or built into the instrumentation. And how do you show that? And that's kind of the converse of the problem of how do you show that the system that you detected actually is like that, actually does have the parameters and the properties that you're talking about. And so my point is that the empirical checks on that kind of reasoning can be the kind where you just check a set of results against a set of observations or maps, but it can also be the sort of broader set of frameworks where you talk about, well, we know that this particular set of methods are robust in the second sense that you were talking about, because even if you change the way that you're checking the results, or even if you change the way that you're building the models, you get the same result, or effectively the same result. And so it's not something about the models that's leading us to make this conclusion that a system of this type is present. Does that clarify things or make them murkier?
I'm not sure. I'll have to think about it. Because I thought it was clear, but I also think that talking about robustness in terms of variation in the models and the assumptions used in drawing the conclusions is also arguably to be unified with variations in other aspects of the methods in the first kind of robustness. But there's another question, so I'll talk to you more later.
That sounds good. Thank you.
We have a question from Bill.
Thanks. Great talk. Really enjoyed it. Sort of a comment first. Near the beginning, you had a slide from a scientist's paper that suggested that population synthesis was a new kind of method in science. And it struck me, well, wait a minute, what about, I don't know, cladistics or evolutionary geology or something like that, right? Why isn't that similar? But that's not really my main point. It just occurred to me. So I guess my question is about something you said about halfway through about the similarities between the population synthesis models and observational maps and so on, right? So it strikes me that assessing similarity between those kinds of systems is going to be problematic, in part because analogical reasoning is always difficult, right? And human beings have this tendency to see patterns where there might not really be any, right? We see sheep and puffy clouds and things like that. So how do we assess whether the models are really like the observations?
Yes. The easy question. Yes. So, yeah, and a question that I studiously avoided, which is the question of realism, right? And I'm, you know, how do we know that this is really what's there? So, okay. The question. So first of all, I think that there are two separate questions. So one question is, how do you compare the results of population synthesis with large-scale maps? And I think that already is a difficult question, because maps are often measurements at a particular time, whereas the whole point of population synthesis is that it's an evolving picture, it's a dynamic picture. And so there are the same kinds of really fascinating problems that you get elsewhere, namely, is this really a star at the stage of evolution that the model says it is, or is it actually a different kind of star at a different stage of evolution, and it's just that it looked like the other kind, right, because of the way that it was put together. And so there are those kinds of problems that are kind of just very bread and butter scientific problems. How do you tell that this is actually a star of this particular kind, right? And you can make mistakes and so forth. But I see those as kind of problems in drawing an analogy between static and dynamic models. That's, as you say, that's a problem that comes up in all sorts of sciences, and it's just a known problem. The sort of deeper problem is, how do you, if you have two methods of simulation and they overlap in part, but they don't overlap completely, how do you know that the places where they overlap are actually meaningful and that you're actually finding some kind of meaningful connection there, right? Because I tried to be sort of constructive in the talk, but if I wanted to be destructive instead, I could say, look, both of these research communities use variables or parameters. How do we know that they're the same ones, that they're being measured in, you know, how do we know that like what one set of equations calls mass is the same as what another set of equations calls mass or luminosity or whatever? And this is a known problem. This is not, I'm not making this up, right? And so in a way, this question gets to the heart of what I want to argue, which is that the way that you establish that is by building a framework where you can make a deeper argument than simply saying, well, there's a match between these observations and these observations, right? So you can make an argument where you say, look, there's actually like a structural similarity between the way of modeling these phenomena in population synthesis and what was picked up by the detection. And you can actually show that that similarity results from something that you can argue, making a substantial argument, and it'll differ in each case, but where you can make a substantial argument that in fact these are the same thing. And so then in answer to what's sort of behind your question, I think that's why you can argue that there's a real thing there, is because you can make this deeper argument that in fact, it's not just that we've made this, it's not just that there's an observation that confirms the theory in some Popperian sense, it goes beyond that. There's an aspect of the framework for deriving this result on this side that maps on in some substantive way to the way that the result was derived on this other side. But those two frameworks are in some meaningful way independent of each other. And so they're reinforcing each other rather than dependent. So that's really what I'm trying to get my fingers on. And it's kind of a sticky question, but I take it that that's the idea.
That's great. Thank you.
Thank you.
All right, so I don't see any more questions. So let's thank Lydia for an excellent talk once again.
Thank you. Thanks everyone for your questions.
Yeah, and we will see you in a week. Thank you.
Okay, bye-bye. Thanks a lot. Bye-bye.
Take care.